that we've done, we have been dealing with balanced forces. And what that means, for example, is in our situation with a block where we had the spring and we were pulling it, the block was moving at constant velocity. And let's remember the constant velocity means in a straight line at a constant speed. And what would happen in that case is that we had the normal force on the block being balanced by the weight, because if it weren't, what we do is we'd see this block go upwards if the normal force were bigger, or if the normal force were smaller, we'd see the block crash through the table. So we knew that the forces were balanced in the y direction, but also in the x direction, because this is moving at constant velocity. What we were able to say is, well, when things are moving at constant velocity, no net force acts. And of course, net force means the total force from everything, and that means in this case it cancels. So we had the spring force, or this applied force, and we had the friction force. So what we had was two situations. We had the vertical forces canceling, and we had the horizontal forces canceling. And of course, in your worksheet, you had problems where I had you calculate the difference between the applied force and the friction force. And what we want to do in the lab that I'm going to have you do tomorrow is we're going to actually deal with the situation where what we're going to have is vertical forces, where we're going to have a normal force on the mass due to the floor, and we're going to have the weight of the mass due to the earth. And we're going to look at situations where weight is bigger than the normal force. We're going to look at situations where weight is less than the normal force. And we're going to look at situations where weight is exactly equal to the normal force. All right, that's the bell. Anyway, so these are the three situations that we're going to look at. Now, in this situation, I actually want to define something, because the way we're going to measure the normal force is we're going to actually have you stand on a scale. And when you think about it, that makes perfect sense. You read a scale to get your weight. So you read this to get your weight. And what you're really reading is the normal force. That's what the scale measures. It's measuring the force that the scale is putting on your feet to hold you up. And so when we talk about the lab that we're going to be doing tomorrow, what we're really going to do is we're going to put you on the elevator. And you're going to read the scale, and the term that we're going to be using to describe the normal force on the elevator is the term apparent weight. So we're going to be using that term, and what we're going to do is we're going to have you ride the elevator with the scale, read the scale, and then talk about what happens when the forces are unbalanced this way, where the weight's bigger than the normal force, unbalanced this way, where the weight's less than the normal force, and when they're actually completely equal. So we're going to be doing the elevator lab tomorrow, and we're going to be covering these ideas in class. And what we're going to do as a result of this is we're going to come up with a new equation from the elevator lab to describe unbalanced forces. And this is what Newton's second law will be. We're going to write down an equation to deal with unbalanced forces. And that's what Newton's law is about. Newton's law is about unbalanced forces. And so our goal tomorrow is to do a lab in an elevator to figure out how to come up with an equation for unbalanced forces. All right, so I wanted to just go over that problem that we did in class today, because this is the kind of thing that we need to get into, because we're dealing with forces at angles. Now, from last semester, you know how to draw a free body diagram for this system. We're going to have the force on the desk because the person pulls it. We'll have the weight on the desk due to the earth, so the weight of the desk due to the earth. we have the normal force on the desk due to the floor that it's resting on. And since it doesn't move, we actually have a static friction force that keeps it in place. Now, here's the key to this problem. I'm going to draw something and then I'll actually erase it, which is that we have this force pointing at an angle of 30 degrees, like that. Okay. Now, here's the key to solving a problem like this. You see, in the last class, we dealt with that friction lab where we had the spring, and of course it was very easy for us to say, oh, well, the spring force is this way and the kinetic friction is that way, and it was very easy for us to see that the spring force and the friction force balanced. That was super easy for us because everything was nice and neat. We have a problem here that this force points at an angle. So here's what we're going to do to get around that difficulty. First, let's just take this force and we're going to move it over here. And we'll clean it up a little bit because I want to get rid of a couple of things here. Just get rid of this weight. Good. So we don't need that little weight there. We just got this force. Now what's happening to it, let's actually do what we did in class. We're going to split this into its x and its y components, just like we did in class. So we know that it's pointing at 30 degrees. So here's what's going to happen. We're going to calculate here. We're told that it's a 200 Newton force. So we know from our formula that F dP in the x direction is 200 times the cosine of 30. And in the y direction, we can actually go ahead and get that. In the y direction, that's going to be 200 times the sine of 30. So when we put that in our calculator, remembering to be in degrees, we're going to get 100 newtons in the y direction and 173 newtons in the x. So here's how we're going to take all this information and put it here. So first, I'm going to have F dP in the x direction. That's going to end up being 173 newtons. And then here, F dP in the y direction, supposed to be a y, that's 100 newtons. So you know what I'm going to do is I'm going to get rid of this little degrees thing here, just get that out of the picture. So now all we have is horizontal and vertical forces. So now that we've split this into its components, what we're going to do is we're going to actually ignore this guy here. I've scratched it out there. In fact, leave it in the picture, but I'm saying like conceptually I'm just going to ignore this guy now. So I'm going to ignore it now. And instead I focus on this guy and on this guy. So it says write the equation that describes the forces that act in the x direction. So what I'm going to do is I only read horizontal forces, and I know that they have to balance because we're told the desk doesn't budge. So we write the equations down. So we're going to have F dP in the x direction, and we have friction going backwards, and the effect is that those forces cancel out. Okay, this 0 means nothing happens. They balance. Now in the y direction, I read this off the picture. I have the normal on the desk due to the floor, and I have the y component of the force on the desk due to the pulling. So I've taken care of those. Now, pointing downwards, I have weight, and it's actually all three of those forces that balance each other out. So again, this balances and that balances, like that. Now what's funny is they ask us for the x and y components of this tension force. That's this. This F dP, that's what they mean by tension. So we've actually already got those. We already know that the tension, that's F dPx, that's going to be 173 newtons from here. And in the y direction, that's going to be 100 newtons here. Now it says determine the value of the frictional force. We're going to use this equation here. So we're going to use the x equation. So when they say determine the value of the frictional force, they really mean use the x equation. So let's go ahead and do that. I'm going to write, so I'll just go ahead. I'll just recopy it. right here. And so when I plug in my numbers, I will actually get that 173 newtons minus the frictional force equals 0. So I'm left that the static friction equals 173 newtons. Now, it says do the same for the normal force. So you know what? Let me just move this answer right here. I'll move this over, move this up a little bit, and put all this here. Now, for the normal force, we're going to use the same idea. So let me just go ahead and try to just, whoops, sorry about that. Try to get this equation, that back where it belongs, right here. Excellent. So now I'm going to plug in my numbers. I don't know what the normal force is, but I do know the following. For the weight, I put in mg. So I'm told that it's a 50 kilogram desk times 9.8. Let's go ahead and get that. And 50 times 9.8 gives me a 490 Newton desk, because that's just plain old mg. Now the force I'm told here, I calculated it already. I know that that's 100 newtons. So now what I can do is I can go ahead and solve. So I get that the normal force plus the 100 newtons from the pulling force of the person on the desk minus 490 newtons equals 0. When I solve, I'm going to get that the normal force is 390 newtons of force. And that's basically the idea. So I'm going to actually have you do number 6 on the Google Docs. And this is kind of a good guide for you to get started. So hopefully that helps you out a little bit more.